We're going to review for exam 6 today on chapter 17, which is basically the second law of thermodynamics. And I was just looking at the syllabus schedule. That means May 3rd will be this exam, and on that day we'll do chapter 18, the last chapter of the semester. And we won't have a face-to-face review. The only reason being that the next day available day is in the final week, and by law I'm not allowed to do any teaching then. It's all finals. So what I've got is I taught this course last summer and have a review recorded for chapter 18. So that's posted in Blackboard and you'll have access to it. I've looked at it and the quality is okay. I mean, it's about what I'm doing now with recording quality. So I think it'll suffice. You just have to review that video for chapter 18. All right, so there you should be able to see version 2. And it's, let me see here. Scoot that over. The problem with this laptop is the screen's smaller than my home computer. So that's going to be a challenge. All right, I'm going to start with problem number 2. Why don't I just, yeah, I think I'm going to just minimize this screen if I can. That's better for me. Okay, this is version 2 and number 2. All right. So we've got a flask with 2 bulbs on it, and in these flasks, doesn't matter what size they are, we have 5 particles. Okay, it doesn't matter where they start from. The question is, what's the probability of finding all 5 particles on one side? Right? This is a statistics problem, and it's designed to get you to think about the true nature of entropy. Entropy is really, thermodynamics, in fact, is really an exercise in probabilities. So if any of you have had statistics, this will be familiar to you. If you haven't, it's not that complicated. Really, it's kind of like flipping a coin. If we just start with 1, say, what's the probability of finding A on this side or that side? Well, you've got 2 possibilities, and only one at a time can happen. So really, the probability of finding A on either side is 1/2. Okay? What's the probability of finding B on one side or the other? Well, it's the same thing, right? 1/2. Okay, you can do that for each one of them. What's the probability of finding both of them on one side or the other? Well, if the probability of finding one on one side or the other is 1/2, and the probability of finding the other one on one side or the other is also 1/2, the probability of finding both of them on the same side, in this case we're saying the left-hand side, is the product of those 2 probabilities. I heard a ding-a-ling. Let me see who showed up. Ah, Galen. Okay, good.
Yeah, it's me. I was having computer issues. It didn't want to load.
Oh, you too. Yeah.
Yeah.
Yeah, I had a power out this morning and my home computer is not functioning.
Yeah, this one, I don't know what's going on with it.
Yeah. I'm working off my laptop now. That's why it looks a bit different. Okay. So, I hope you can see where I'm going with this. So if we do each one in turn, the probability of each one is a half, right? A, B, C, D, and E. So the probability of finding all 5 of them on one side is 1/2, actually 1 divided by 2 to the 5th power. Okay. So what's 2 to the 5th power? Well, the first power is 2, 4, 6, no, 2, 4, 8, 16, 32. So we divide that by 32. And I already know the answer, so I'm just going to put it up here. So if you convert that to percent, the percent probability of finding all 5 of them on one side is 3.13%. Okay. So this is the least likely of all possibilities. If this was a physical demonstration with 5 gas molecules, then the probability of finding them on the left-hand side is 3.13%. On the right-hand side, same thing. And you can do similar calculations for, say you want to find 2 on one side or the other. Then you can go through the same manipulations, but it's a probability function. What's the probability of having, what's the highest probability available? Or the most number of microstates is another way of stating it in the physical world. And that's what we were looking for. This is the least likely. In other words, like I said in class, I said in class, I had a professor who said, who was trying to explain probability. He says, there's a very, very, very small probability, vanishingly small, that all the molecules of air in this room will migrate to that corner and we'll suffocate. Right? It's true. It's probable, but it's not very likely because it has a very low percent of happening. Okay, that was number 2.
Okay, now Dr. Bly.
Yep.
I know you're erasing it.
Oh.
But if it was if there were only 3 particles on one side of the flask, would we just the product of 1/2 times 1/2 times 1/2?
Exactly.
Okay.
Yep.
Just making sure.
So that's a good point. If you have a mole's worth of particles in those flasks, then the probability of finding them all on one side is, I mean, it's just vanishingly small because you have 1/2 to the mole power. Okay, that's an extremely small number. Okay, so that was number 2. Let's see. I'm going to skip to 14 now. Let me see. I'm trying to adjust to a failure in technology here. All right. I might have to use my little mouse pad because my normal mouse is covered up. Oops, let's do this. I don't like mouse pads, but sometimes you have to use them. Okay, so there's number 14. Okay, for this process, CHCl3, which is, by the way, chloroform, from the solid to the liquid, that transition, and we're given the delta H and the delta S for that. So if we go from solid to liquid, the delta H, the standard delta H, in other words, 1 atmosphere pressure and 25 degrees Celsius, that value is 9.19 kilojoules. And the delta S for that process is 43.9 joules per mole K. Notice these are both positive signs. So that means that this is an endothermic process, which makes sense. You're going from a solid to liquid. You got to put energy in to break those bonds, all the intermolecular bonds that are holding that solid together. And also the delta S for the system, right? When we don't write something down here, we automatically mean system. So the delta S 0 for that system is also positive. We're going from a solid to a liquid. So it's more disordered, which stands to reason. Okay, but that's not the question. The question is, what's the melting point? What temperature is melting point? Okay, remember when we said earlier that delta S for the surroundings equals negative delta H divided by temperature. Right? That's always true, no matter what the situation. But under certain conditions, this is also true. Okay? For the system, you just change the sign, right? Because if the whatever is happening in surroundings, the opposite is happening in the system. But there's only one situation where that happens, when you're at an equilibrium situation. And phase change is considered equilibrium in thermodynamic terms. And here's the way it looks, right? Delta S total is equal to 0 at phase change, because all the energy is going into breaking bonds. It's not going into adding energy entropy. So if that's the case, then this one plus that one, right? Those two together equals 0. So under those circumstances, if one of them's a negative sign, the other one has to be a positive sign in equal magnitude. They cancel each other out. So if this is true, and this is a phase change, now we can do a calculation to find out what this T is, because we have this one, we have that one, right? So let's just plug in some numbers. Let's see, I'll erase that one. So delta S for the system is equal to delta H divided by T. Now, what else is a problem? Units of measure. That's in joules, that's in kilojoules. It's easier to convert to joules. So I'm just going to say, we take this K and we put it over here. Make it 1,000, right? So now this is gone, and that's joules. 9.19 times 10 to the third. So we have this one, 43.9. I'm going to leave the units of measure out because of space. And 9.19 times 10 to the third divided by T. So now how do we get T? Well, just a little algebra. Move the T over here and move that value over here. So we divide this one into that one, and we get T. Let me pull out my calculator. I know the answer's sitting right there, but I like to do it just to keep me in practice. 9.19 and exponent 3. Okay, and then divided by 43.9. That's 209, three significant figures, 209K. All right. And our answers are in Celsius. So we have to subtract 273. So let's say 273 subtracted is minus, oh, okay. Significant figure rules. Up to this point, it was multiply, divide, right? So we had three significant figures here. But now we've got add, subtract rules. And there you match the decimal. So when we subtract this one from that one, we're left with two places, ones and tens. So it's rounded off minus 64. There you go. So that's why the answer is A. Okay, that was 14. See, I'm still on screen. That's good. 14. Now let's skip to 20. All right, let me see. I'm going to have to, where's my, there it is. There's 20. I think that one's about gone. Where's my trash can? All right, in which case must a reaction be spontaneous at all temperatures? All right, what is that question saying? It's saying the reaction has to be spontaneous. And any temperature. Okay. What do we know about spontaneous? We know that if we can calculate delta S total, a positive value there would be spontaneous. But we can't. Not with the information given. Notice here, we've got delta H and S, delta H and S, delta H and S. So that ought to be a clue right there. If the answers are in terms of delta H and delta S, both, then we're looking at Gibbs free energy. So if it's spontaneous, Gibbs free energy must be negative. And that is equal to delta H minus T delta S. Right? So, under what conditions would this always be negative? Well, it would be nice if both of these terms were negative. Right? If that's the case, and I'm talking about, no, let me make a correction here. There you go. If that, well, actually, the whole thing is negative, but what is, yeah, if the whole thing is, actually, the whole thing needs to be positive, right? Because we multiply it by a negative, then we get a negative, and that's equal to negative. So, and temperature is in Kelvin. It's always positive. So delta S is the only fly in the ointment. What is delta S? Well, if delta S is positive, then times T times a minus gives you a negative. And it doesn't matter what T is. If delta S were negative, then the only time it would matter is if T was very, very low. So this term would be almost nothing. Then that negative would dominate. Or if this were positive, then that T would have to be very large in order to give you a negative large enough to overwhelm it, right? So the only situation where it doesn't matter what the temperature is when delta S is positive and delta H is negative. So you have an increase in disorder and you have an exothermic process. Then the temperature doesn't matter. It's always spontaneous. All right, let's see which one matches that. It looks like delta H is negative, right? If delta H is positive, it won't work. If delta H is 0, it won't work. If delta S is 0, then that depends on delta H. But if delta H is positive, right, then it's not spontaneous there either. So the only one that fits, it looks like, is delta H is negative and delta S is positive. Yep. That's D. All right, that was 20. Let me see where I'm headed next. 26. Let's see here. Let's go on down to 26. Oops, went too far. There. There we go. All right, I'm scooting the board around here. Let's see, fix it. There we go. All right, 26. When a stable diatomic molecule spontaneously forms from its atoms. So what are the reactants? The individual atoms are the reactants, and the diatomic molecule is the product. Right? So we've got two atoms, doesn't matter what they are, spontaneously forms a diatomic. There we go. That's the equation. And the other key word in here is spontaneous. Right? If it forms spontaneously, you already know delta G. Right? So if we have these possibilities, like the answers are like this, delta H, delta S, and delta G, we know delta G is negative because it says spontaneous. Right? So that means B or E. Either one of those could be the answer. So let's look at the others. Right? What about this as far as the disorder concept? You're going from 2 to 1. It's getting more disordered or less disordered? It's getting less disordered. It's going from 2 individual atoms to 1 molecule. Right? Okay. So how about delta H? What do we know about heat and reactions? Individual atoms that come together and form a compound always give off energy. Otherwise, it wouldn't happen. In other words, this is more stable than that. This is an exothermic process. When you form a bond, it gives off energy. So they're all negative. That means the answer is E. If we knew something about the temperature, then we could use Gibbs free energy equation to figure out the delta H. But we don't have that information. I was looking to see if there was another idea. Sometimes you can solve these problems with more than one. No, that's the best approach. Okay, that was 26. Let's see, what do I have next marked? Let's skip over 31. So let's go to 31. Okay. There we go. All right. Question says, well, it's an instruction. Calculate KSP for the salt sodium chloride at 25 degrees Celsius. So we need the KSP, which is solubility product. Right? So what does solubility product mean? And this is an equilibrium expression, you remember. So solubility product means the solid is going into solution. So that means sodium chloride solid, right, is producing sodium ions in solution plus chloride ions in solution. Right? So there's our equation. And they want us to calculate KSP from that data, right? We're not given any concentrations here. So we have to approach it a different way. What do we know about the KSP? We know that under standard conditions, 25 degrees Celsius, 1 atmosphere pressure, and 1 molar concentration, we know that delta G 0 is equal to, I think it's minus RT log K. Remember, that was derived from the expression for delta G equals delta G0 plus RT log Q. And then under conditions of equilibrium, delta G, the actual delta G, is 0. So then we solved it for this, and that's where we got that equation. So what do we need? Well, let's see. We have the temperature. Right? We just need to convert it to Kelvin. We have the R, 8.3145. And we just need delta G so we can calculate K, because this is KSP. All right? So what's delta G? We have to calculate it, right, from that information that's given. If we know the delta G's for formation for each of the components here, then we can calculate delta G for the reaction. Right? Remember, delta G0 for the reaction equals the sum of the delta G0 of formation for the products minus the sum of the delta G0s for formation for the reactants. All right. So all we have to do is go to that table and say we need this one. Which is minus 262 kilojoules, right? Minus 262, and there's only one of them. You would have to multiply this times any coefficients, but all of our coefficients are 1. That makes it easy. And then we're going to add a negative, well, might as well just say negative, 131.0 for the chloride. And then we subtract the sodium chloride solid, minus 383.8. Minus.
Dr. Blah, I hate to interrupt. What did you write above that?
Where?
I didn't really. The delta G equals,
Right here?
yeah. What is that entire thing?
Oh,
I got lost at that part.
okay. That's a sigma, which means
Cool.
summation. You add together all the delta G's of formation for the products. And then you subtract the sum of all the delta G's of formation for the reactants.
Okay.
Okay?
All right. Thank you.
So in this case, we have two products, so we have to add those two together. And then we subtract whatever the reactant is, which is minus 383.8. And these are all in kilojoules per mole. And then if you multiply by 1 mole each, then that gets rid of the moles. So you really only have kilojoules left. Okay, so delta G then for this reaction is, let's see, 262 is a negative sign, and then 131 is also negative. Let me do that again, 262, enter, and then 131. Okay, this is going to be a positive, right? 383.8, which is minus 92. Minus 92 kilojoules. All right. So now that we have delta G0, we can put it in that previous formula. Don't want to erase that yet, otherwise I'll forget it. So now we have that previous formula, delta G0 equals negative RT log K. So we know this one is minus 92 kilojoules. Oh, there's another problem. The R value is in joules. So we need this one in joules. So let's take that K. There we go. Now we've got joules. Then minus 8.3145. And this is joules per mole K. And then we have temperature, which is 273 plus that is 98. 298. Right, so the K's cancel. And then we have log K. So now we have a problem we can solve because there's only one unknown. Right? We just take this one, divided by that negative, and divided by that. And that gives us log K value. So we're not done yet. So let's say, make my correction for joules here, and then divide by 8.3145, negative sign, and then divide by 298. So I get 3.713. Log K equals 3.713. And how do we resolve this? K equals E to the 3.713 power. That's how you would do it in your calculator. Just use this as the power of E. So mine's already sitting there. I just need to punch the right button.
So
Let's see.
that's negative 92. I can't see what you did right there with the joules. It's kind of blared out. Go on up where it
Here?
says negative 92. Yeah, did you multiply it or?
Yeah, there was a K here.
Okay.
And I took that K and I turned it into 1,000. That makes joules.
Okay.
Okay.
That makes a lot of sense now.
Yeah. Is the video not the quality that you're used to?
No, I thought, no, this is fine. I thought it was glared out.
Oh no.
Okay.
I
Okay.
actually erased the K and turned it into 1,000.
So you just converted it. Okay.
Yeah, kilo, 1,000. And that makes, actually, that's redundant to put that there. I should have moved this over here. Minus 92 times 10 to the third joules. And then I divide this by that one and divide it by this one. And that leaves us with that calculation is equal to log K. So then K is e to this power. And let's see. Looks like two significant figures. I get 41. K equals 41. And K doesn't have any units of measure anyway. So that's why the answer is A. So what does that mean? Once we determine that 41, what does that mean for the actual solubility product? That means it's hugely soluble because that number is so big. Much, much greater than 1. And this also tells us delta G is negative, a very large negative number, which means it's spontaneous. It's very spontaneous also. There's a big driving force for that solid to go in the solution. All right, that was 31. Let me see what's next. 34. 34. Here we go. So let's make room. There we go. All right, now I need to scroll down. 34. Here we go. All right. So we're considering the gas phase reaction. Everything's in the gas phase of NO plus 1/2 oxygen yields NO2. Okay. And what are we given? Delta H. Delta H 0 is negative 56.91 kilojoules. And we're also given K. K is equal to 1.46 times 10 to the 6th at 25 degrees Celsius. Okay, that's everything we're given. Now let's look at the question. For this system at equilibrium, all right, so we're establishing now at equilibrium, what will happen when we raise the temperature and how will it affect the concentration, the amount of this one right here? Okay, we don't have to do a lot of fancy calculations. We got numbers, but the only number we need to focus on is not the number itself, but the sign. The sign says this is exothermic. So what does that mean? That means in this equation, where do you put the heat? If it's exothermic, the heat's coming out as a product, right, without the sign. So now we can make a prediction. What happens when you increase the temperature? You raise the temperature, you're adding this component. And Le Chatelier says if you add something on this side, it's going to shift back that way. So now we're increasing the amount of NO. The amount of NO will increase. Okay? Now, in reality, when you change the temperature, you actually change the value of K. Yep, you do change the value of K. So Le Chatelier sort of crosses over from one side to the other.
What if delta H was positive?
Say again?
What if delta H was positive?
If delta H was positive and you increase the temperature,
Yeah.
it would be over here. Delta H would be on this side. It would be endothermic. So if you put delta H over here and increase the temperature, you're driving the reaction that way. And then NO would decrease.
Okay, that's what I figured.
Yep.
I'm just trying to get a full understanding of this.
Oh, that's good. Questions are good. Okay, that was 34. Let's see. Next one I have marked is 40. Let's scroll down to 40. Now, I'm not saying all of these problems are not good to work. It's just in the limited amount of time we have, I thought these would be the best for understanding the material. Well, maybe not the best, but there's a good mix for understanding the material. 40. Oops. Okay, let's change that one. Here we go. The second law of thermodynamics states, okay. Now, this may be in literal verbiage that we've been introduced to, or it may be twisted a little bit, but we're looking for the meaning of the second law of thermodynamics. So let's just say second law is what? In its simplest form, the second law says delta S for the universe is always greater than 0. Okay? For the entire universe, I mean the real universe, delta S is always increasing. But if we isolate system and surroundings so that we get an exchange between the system and surroundings and no influence from the outside, then we have a different situation, slightly different. In that case, delta S total, right, for that isolated system surroundings is greater than 0 when? For spontaneous reactions. Now, I guess technically you could say that since delta S for the universe is greater than 0, then all reactions are spontaneous. But not really. All reactions taken together create a spontaneous situation. But you can have isolated pockets of spontaneous running backwards, and where this would be negative. So that's not a good approach. I mean, that's true. Don't get me wrong, that is true. But this is more useful. The delta S for the total, which is system plus surroundings, is greater than 0 for spontaneous reactions. Okay, so let's see if we got one here that fits. Energy is conserved in a spontaneous process. That's not the second law. Closer to the first law, right? Energy is always conserved in a reaction, whether it's spontaneous or not. How about B? The entropy of the universe increases during a spontaneous process. Okay, here's a problem in semantics. And since I accepted these problems from the publisher, then the wording, in my opinion, is a bit off. The entropy of the universe, I say the entropy of the total entropy of your isolated system surroundings increases always during a spontaneous process. And with that interpretation, B is correct. Well, let's see if there are any others that are better. Well, there's only one other one, right? The heat content of the universe increases during a spontaneous process. Is that true? Not necessarily. During a spontaneous process. If you look at Gibbs free energy equation, you find that it can go the other direction, right? You can have the heat content, and there we are again with that stumbling block universe. What they should have said was total, right? The authors dropped the ball on that one. The heat content, the total heat content, doesn't necessarily increase during a spontaneous process. It's the balance of heat and entropy that determines Gibbs free energy. Right? So I guess really the one that satisfies best is B. All right, that was 40. Let's see, 42. Scroll down. Let's see, is everything on screen? Oops, that's good. Okay, 42. Pull myself together here too. All right. For 42, it sets up a problem. We have a mixture of hydrogen and chlorine. Right? Remember, hydrogen and chlorine are both diatomic. So you got this mixture. And they're stable. They could sit in that bulb, right? They're both gases, so they have to be enclosed. They can sit in that reaction vessel from now to eternity, and they won't react. Right, so you can have H2 gas plus chlorine gas, and they won't react until when? Until they're exposed to ultraviolet light from a burning magnesium strip. So this is right, energy, Planck's equation. They're supplying energy by the frequency of light from ultraviolet. Ultraviolet light. Once you supply that, then the reaction goes very rapidly. Okay? Oh, wait a minute. I didn't put the products. There we go. Hydrogen chloride gas. Right? This is not hydrochloric acid yet, because we didn't put it in solution. It's hydrogen chloride gas. All right, with these values, delta G is negative 45, delta H is negative 44, delta S is negative 4.76. Okay. We could not deduce that delta S was negative because that's 1 mole, which is 2, and that's 2 moles, right? So we can't say, based on that, that delta S is negative. This is a measured value. So delta S turns out to be negative. So this must be a product of energy entropy to give you that negative value for delta S. Which one of these following statements is consistent with the information? Well, let's see. What's A? Well, A says the reactants are thermodynamically more stable than the products. Is that true? Delta G is negative. If they were thermodynamically stable, right? Yeah. If they were thermodynamically stable, that would be a positive, right? Because it would not be a spontaneous reaction. They would be stable right here. But with this negative, that means they prefer to be over here, thermodynamically speaking. All right. So this one's false. How about B? B says the reaction has a small equilibrium constant. Okay. How do we calculate that? Well, if it's an equilibrium, if we're saying equilibrium, right, and we would have to say that these values are standard state conditions. That's the only way we can solve the problem. If delta G0 is equal to negative 4554, kilojoules per mole, and that's equal to negative RT log K. Then we can plug in values here. We have to change this to joules because of that term right there. So here I go again. I'm going to take that times 10 to the third. And then R is going to be, well, I'm just going to put the negative there, 8.3145. And the temperature is 25 degrees, correct? Does it say? Then the following reaction occurs. Well, we don't have any choice, right? If it's not 25 degrees, then we're stuck because we don't know what the temperature is. So we have to say 298. That's 25 degrees Celsius. And then log K. So we solve this one the same way we did the first one, the previous one. We take this value and divide by that and divide by that. And then that value is the power of E. So 45.54 negative to the power 3 power. And then we divide by 8.3145, change the sign, divide that into it, and then 298 divide. Okay, so I get 18.380, 18.380. Equals log K. K then is e to that power, which is 9.6 times 10 to the 7th. All right. And that was B. The reaction has a small equilibrium constant. I don't think so. Not 10 to the 7th. It's got a huge equilibrium constant. All right. So that one's false. How about C? The ultraviolet light raises the temperature of the system and makes the reaction more favorable. It doesn't raise the temperature of the system. It just supplies energy. By the way, what energy is it supplying? UV is supplying activation energy, right? Just a little bit of light from that burning magnesium strip. Even if it was inside the bulb with them, it would not raise the temperature that much. I mean, it is exothermic, but all you need is a tiny amount. So the heat produced by it is almost inconsequential. The real thing that you're looking at is ultraviolet light. And when you conduct this reaction in reality, these two gases are in an enclosed vessel that's transparent, or it has a transparent window so that you can shine ultraviolet into it. You don't even need a magnesium strip. I mean, you can use a black light and just put it up next to the window, and that kicks the reaction. That activation energy is being supplied. It's not temperature change. So C is also false. All right, how about D? The negative value of delta S slows down the reaction. D. Delta S negative slows the reaction. What's wrong with this picture? We're talking about thermodynamics here when you're talking about delta S, and it says nothing about speed. Changing the reaction, making it faster, making it slower, we don't know, because it doesn't address that question. Thermodynamics does not address that question. So it looks like the only one left is E. So let's see if E is true. The reaction is spontaneous. Yes, it is. Excuse me. Well, yeah, yes, it is right here. Spontaneous. That's true. But the reactants are kinetically stable. All right, so we are mixing things together in this question. The truth is, it is spontaneous. We know that because delta G is negative. But how do we know anything about the kinetics? Remember, kinetics of a reaction is determined by the activation energy. Right? That was the Arrhenius equation that we studied earlier in the semester. If the activation energy is lowered at any given temperature, then the reaction speeds up, because now you have enough energy to activate more reactions, more individual mole by mole reactions. So yes, the reactants are kinetically stable. As long as we don't supply the activation energy, they will sit there. They may be thermodynamically favored to go that way, but without the activation energy, the speed of the reaction is snail's pace. So E is true. All right, that's the answer. All right, that was 42. Let's see, do I have any others marked? 52. All right. 52. We're doing good on time, I think. All right. Let's scroll down to 52. All right. You should always, in every science course, no matter what kind of science course, you should always encounter periodically graphs and how to interpret them. This is one of those cases. So this graph, I'm not going to try to draw it, is a plot of 1 over temperature, the inverse of temperature, and this is Kelvin, of course. It's plotted as the independent variable, and the dependent variable is the natural log of K, the equilibrium constant for the reaction. So we said earlier, and this is a verification, the K of the reaction actually changes with temperature. Okay, now, how do we express that in mathematical formula? Well, we need a straight line formula. And I'll go back to the one that we were given. Let's see, 52. Put that up there. Is the log K is equal to negative delta H0 over R times 1 over T. There's your X value. There's your Y value. What's this? That's the slope of the line. And plus delta S0 over R. That's the y-intercept. Okay? So you can get a lot of information out of this graph if you know what the straight line means, right? And that's why it wasn't given to you here, because we want you to recognize the relationship here to here is what? Well, you don't have to memorize it. It's in the useful information, right? So let's see, for CHEM102, you have Blackboard exams in Respondus Lockdown Monitor. So what you need to do is go into that folder in your regular browser and find the useful information that's given. Anything in that folder with the exam is fair. Print it out if you don't already have it printed. A periodic table, useful information. There may be some couple other tables in there also. But it's fair to have that with you during the exam. The reason I say go in there first is because once you get into Lockdown Browser, you don't have access to that information. It locks you out of everything except the test. So I want you to have that information, and in that useful information table that's also in the review document, you'll find, I think it's in the middle toward the bottom, there's this equation right there. So you don't have to memorize it, you just need to know how to use it and to recognize when it's applicable. In this case, we have the slope and the y-intercept we know right from here. Now, what's the question? What's delta S0 for the reaction? All right, so what part of that equation do we need? Right there. So can we find that from this plot? Oh yeah. Delta S0 over R equals, where's the y-intercept? 3.0. Right there. So now we know what R is, 8.3145. We can just solve for delta S0. We just say 3 times that value. Let's see, 3 and then 8.3145. We can do an estimation, right? What's 3 times 8? 24. But you got like a third more. So a third of that is 1, 24, 25. I bet it's 25 times. Rounded off, it's 25. Delta S0 equals 25 joules per K mole. Okay? And that's C for the answer. I got a sneaking suspicion I'm going to need that one again, so I'm going to leave it there for now, unless it gets in the way. Then I'll erase it and put it back up later. All right, that was 52. So let me see. 56. 56. Okay, I was right. I'll show you. 56. It's right there. Okay, let's look at 56. The equilibrium constant, Kp, in atmospheres for a dissociation reaction of dichlorine yields two chlorine atoms was measured as a function of temperature in K. A graph of log K versus 1 over T. Right there. All right, let me erase that big circle, because we may not need it that way. We might need some other part of the equation. Or we might need the whole equation. Who knows? So we make a graph of that, and the slope is given, right? Minus 1.651 times 10 to the fourth, and an intercept of 14.51. Okay. The value of delta H for this dissociation reaction is. All right. So what part of the equation do we need? We're given the slope, and there's the slope right there. So negative delta H0 over R equals that value, minus 1.651 times 10 to the fourth. Right? So we can solve that for delta H. Do we need the actual value for delta H? Yes, we do. The value of delta H for this dissociation is blah, blah, blah. So we need to solve it. All right. Okay, I'm just thinking for a second. So this is 8.3145 here. Right? We just need to multiply that times that. And then in order to find out what delta H is, we got to be sure to remove that negative, right? So why don't we take that negative along with this and put it over here? Right? Now, that's positive. Now we can say something about what is actually inside that variable. So 1.651 10 to the fourth, and divide 8.3145. So I get 1.9, let's see, 4 places. 1.986 times 10 to the third. What are the units? This right here determines the units. Joules per K mole. So this is joules. What's the answer? The answer is in kilojoules. All right. Okay. So let's say kilojoules would be, this would be converted to K, correct? Just make that into a K. 1.986, and that's a positive kilojoules. All right, what did I do wrong? Negative. I did something wrong. Oh my goodness. Rookie error. Nobody said anything either. You must be muted because I don't hear any snickering. Correct? It's in the denominator over here. Goes in the numerator over here. Let's try that again. Now, 1.373. 1.373 times 10 to the fifth joules. So that would be equal to 1.373 times 10 squared kilojoules, correct? I just took 3 exponents out of that and put it in kilo. We're standard notation though. All right, so we need take these two and move them 2 places. 137.3 kilojoules. There we go. B is the answer. Notice multiple choice questions. If I had accepted my error, then I would have picked C. And it's wrong because I did the wrong calculation. That was 56. All right. I don't know if I'm going to need that again. Let me see what I've got picked out next. 57. No, I don't think I'm going to need it. Maybe in version 1, we'll put it back up when we need it. 57. There we go. All right. For a certain process at 300 K, temperature equals 300 K, delta G equals, and this is the actual delta G. This is not delta G 0 because that temperature is not 25 Celsius. 273, 300, no, it's greater than 25. 25 is 298, so it's a couple of degrees higher. So the actual delta G for this reaction is minus 12.2 kilojoules. And the delta H equals, we may not need all this information, but I'm putting it up here, kilojoules. All right. If the process is carried out so that no useful work is performed, right? No work, W equals 0. No work is performed. What's the value of delta G? I'll let you in on a secret. This is a trick question. Just to see if you understand what delta G means. Does delta G change whether we do work or not? No. All that says is that is equal to the maximum amount of work that can be obtained from that process. Doesn't say whether we did it or not. This says that we didn't do it. But it doesn't change that value at all. Delta G is still minus 12.2. Right here. Well, there we go, 12.2. All right, that was 57. Let's see, do I have any others? Nope, that's version 2. Now we'll go to version 1. And we're doing good on time. We'll probably finish early today. All right, so let me stop the share on version 2 and share version 1. I think this is, nope, that's version 2. Version 1, here we go. Yep, there's version 1. Okay. Let's erase all that stuff. Version 1. Number. Okay, what's the first one on my list? Let's see. Number 9. Actually, I'm going to do 9, 10, and 11. 9 and 10 are based on the same process. So we'll do them together. Here we go. 9. Okay. At 1 atmosphere pressure, water is heated above 100 degrees. So temperature is 100 is past 100. What's the delta S for the surroundings for this process? We don't have to actually calculate it. We just need to answer the question, is it greater than 0, less than 0, equal to 0, so forth. Okay. So the process is water. You know, actually, we don't have any liquid water. We've got, that's it. So if we've got this water in our system, and these are the surroundings, and they're isolated, right? Now, in order to heat water further, how are we going to do it? Well, you've got to sacrifice to add energy entropy to this system. Surroundings have to lose. All right. So let me see if there's a better way to explain that. Okay, let's do it mathematically. What expression do we know is equal to this? Delta, oops, it's a dead soldier. Let me try this one. Delta S surroundings equals negative delta H over T. That's always true, no matter what the temperature. So, what is delta H? If we're heating water, that is an endothermic process. So this is positive, correct? Right? Delta H is positive. So the whole term is negative. Right? And the temperature, well, it's above 100. So we just say whatever the temperature has to be, it's always positive, right? It's Kelvin. So this is the only term we need to focus on to say, what is the sign of this one? Well, if that's positive, then this has to be negative. Right? So that's another way of confirming it, that the entropy of the surroundings is decreasing as the energy entropy of the system is increasing. That's what happens when you add heat to it. The energy entropy increases. And this is not an equilibrium situation. You have nothing but water gas in there, water vapor. Right? We're not at the boiling point. All right, so that was 9. Let's see, how's it going to change for 10? Ask a different question for 10. Okay. Oh, now we're looking at what is the delta S for the universe for this process. And here we go with semantics again. Delta S for the universe here, the authors mean delta S total for this process. That's the key. When they say for this process, that means delta S total. So what's happening to delta S total? Well, they may not be equal, delta S total and delta S surroundings. Right? We know this one's negative. But we do know that if it were equilibrium, they would be equal and opposite in sign, but they would cancel one another out. Oh, excuse me. System. The system would be positive. And then delta S total, if it were equilibrium, be 0. But we're past equilibrium. And on the high side of equilibrium now, we are actually adding energy entropy here faster than we are there. And all of this energy that we're adding is not required for breaking the bonds of the phase bonds, the intermolecular bonds. In this case, actually, we're adding more energy than is required. So this magnitude is greater than this magnitude. That means the total would have to be positive. Right. It's all dependent upon the magnitude. At equilibrium, they're equal. So that's 0. But when you go past equilibrium and we're actually adding energy to the system, this is increasing faster than that is, which makes this positive. If we went the other direction, right, you're going backwards, then you would be extracting more energy here, energy entropy here, than you would need here. And this value would be negative. No, I'm sorry. This would be a larger value than that one, and this would be negative. All right. So let's scoot that back over. Number 11. I want to go to 11 now also. All right. There we go. We got it all on the screen. 11. Okay, which of the following is true? I mean, this looks worse than it is. Notice the parallels here. Bispontaneous, they all say bispontaneous. We mean that the reaction or process will always proceed blank. Will always proceed, will always proceed. So now we just, for the first part of these statements, you just need to look, is it right or left? Will always proceed to the right. By spontaneous, we mean, yes, it is. To the right, as written. B, to the left, no. C, to the left, no. D, to the right, yes. Test-taking technique, eliminate the obvious false statements, and then start parsing the ones that are true at this stage, right? So if A and D are true up to this point, then we need a tiebreaker, right? So you go to the next part of the statement. To the right, even if very slowly, that's true, right? Because spontaneous, thermodynamics says nothing about kinetics. Then the next part of the statement, increasing the temperature may speed up the reaction. Okay, it could. Increasing the temperature may speed up the reaction. They both say the same thing. So let's look at the rest of the statement. A, but it does not affect the spontaneity of the reaction. Is that true? Does temperature have an effect on spontaneity? Well, according to Josiah Gibbs, it does. Temperature definitely has effect on spontaneity, right? So, does not affect spontaneity is a false statement. So is D correct? because E says none of the above are true, we got to see, is D true? It's the only one left. If it's false, then E is true. So let's look. Increasing the temperature may speed up the reaction, true, and it generally affects the spontaneity of the reaction. That is true. All the statements in D are true. So there's your answer, D. All right, that was 11. Let's see. Okay. I'm going to skip to Malou. 34. Those in between probably repetitious. Let's see. Yeah, I want to get rid of that thing. There we go. 34. Oops, too far. There we go. 34. All right. So what does 34 have to add to the conversation? For the following reaction, all right, for this reaction, CO2 plus, well, that's a gas, plus water, that's also a gas, is in equilibrium with CH4 gas, that's methane, right, natural gas, plus 2O2 gas. Let's see, we need 2 waters here. There we go. Now we're balanced. Delta H, 0. Standard conditions equals 803 kilojoules. Right, that's everything that's given. So what does that mean? That means from left to right, it's endothermic. Right? You have to add energy to go from CO2 and water to methane and oxygen. Okay. This looks like the reverse of a combustion. We just take that and burn it in oxygen, and you get CO2 and water. Okay. So if we wrote it the other way, this would be negative. You get a lot of energy out of it. But to go backwards, to go that way, you need lots of energy. Okay, now the question. Which of the following will increase K? All right, there are 2 approaches to this. One, first to look at K. What is K? CH4, O2 squared, and then CO2, and then water squared. So if we want to increase this value, we need to somehow, at equilibrium, assure that we have more of this and or more of that. So the reaction needs to be over here to increase the K. All right, let's look at our choices. How about A? Decrease the number of moles of methane. Right? Will that change K? No. It'll change the equilibrium position. It'll move, right? It'll consume some reactants to make more product. But it'll do that until equilibrium is reestablished at that very same K. So A is false. How about B? Increase the volume of the system. What happens when we increase the volume of the system? Well, Le Chatelier says that the system will respond to produce more moles of gas, right? Because you're decreasing the pressure, you're giving it more room. So if the reaction is has different moles of products and reactants, then it'll move to the side that has more moles, right? 1 plus 2 is 3, 1 plus 2 is 3. That will have no effect on this system whatsoever. Plus, that would only change the equilibrium position, just like A, similar to A. Change the equilibrium position, but it would not change K. How do you change K? Change the temperature, right? So that one's false. How about C? Increase the temperature of the system. Aha. Now we're messing with K. Okay? Now, we can actually calculate what the value is if we can plot. If we plot it, I should have given myself some more room here. Maybe I can squeeze it in right here. Right? So this is 1 over T, and this is log K, right? We're messing with K, with T. This is your go-to equation. Now, what do we know also? This is positive delta H. What's the slope of that line? Right. Well, if we look at log K equals negative delta H, 0 divided by R times 1 over T plus delta S 0 over R, then the slope of the line is here. Now, when is that slope going to always be negative? When delta H is positive. When delta H is positive, then that slope is negative. Like that. That's positive. This value is a negative slope. The other way around. If delta H were negative, if it were exothermic, then this term would be negative and the overall would be positive. And it would go the other direction. So if the slope is like this on that plot, you know you have an endothermic reaction. But, and you also know this, right? That's endothermic. But if the slope is this way, you know the reaction is exothermic. Now, I guess at some point you could get a reversal, right? I can't give you an example right now, but I would think it'd be reasonable. Over a certain temperature range, you could go positive and then all of a sudden go negative. That would be a broken curve. Anyway, back to the topic. So what this is saying is, what happens, let's go back to C, increase the temperature. What happens to this term as you increase T? Right? If you make T bigger, that makes this term smaller, so it moves this way, right? Make this bigger, it moves this way. That means you're going up this line, over this way, up that line. Log K gets bigger. So what does that have to do with K? Well, if log K gets bigger, K gets bigger. So increase the temperature of the system, increase K. That is true. Okay? That's one way to solve the problem. A quicker way to solve the problem is to not even use this. We know that changing the temperature is going to change K. But we just need to know, how does it affect these values? So the other way is to say, if it's endothermic, where's delta H? Over here. Okay? Increase the temperature, you plug more of that in there. So what does that do to the equilibrium position? Well, it produces more of this and more of that right here. right? So we can infer that by increasing that, the K is also increased. And increasing the temperature increases K, right? That's not as definitive. I mean, that's a stretch because here we're talking about equilibrium position and here we're talking about equilibrium. But we know that temperature changes the equilibrium constant. We just need to figure out what direction does it change it. And that's what that tells us. So either way answers the question. That was 34. All right, 34, 36.
Hey, Dr. Blah.
Yes, sir.
I just wanted to double check something real quick.
Okay.
The email you sent out about Lab 6, it's canceled, right?
The very last one, the electrochemistry, yes. I had to cancel. I don't have time to do the demonstration.
Okay. And you said if we already sent in our lab notebook pages that they would be graded?
Yeah, you get credit for them. Right.
Okay.
Yeah. I think I've already got yours.
Okay. I figured because I turned it, what is today?
It was last week sometime, wasn't it?
Yeah, I think it was Thursday or Friday of last week.
Yeah.
Oh, it was Friday because I remember thinking you wouldn't get them because you're always out of town on Friday.
Under normal circumstances, I would be out of town. I'd be in Logan. But Logan's in lockdown too. So I have to teach.
I didn't know that.
Oh, yeah. I have to teach those
Wow.
courses remotely, the same as I'm doing this one.
Okay.
Yeah, mine's almost finished, so I'm going to submit it too.
Okay, that's fine. That'll be a boost to your grade. I mean, if you have to make 80%, you might as well go for 100.
Yeah.
And that boosts your grade. And most people need a boost to their grades right now if you've checked your balance lately. Let's see, where was that? 36. So you can get back down here. 36. Most of the problem I say about the labs, most of the problem people are having now who are really in serious trouble haven't turned in their work. Right? If you've turned in your work, then there's still hope. But if you haven't turned in your work, your ship is sinking. The Titanic is on the way down. Okay, 36. Consider the gas phase reaction. All right, we looked at one of these earlier, I think. I remember the phrase gas phase. Only this time we got NO plus 1/2 O2. You know, I think this is we have looked at one like this before. NO2. NO2. So that's a gas, and that's a gas, and that's a gas. That's what they mean by gas phase reaction. It's homogeneous. All reactants and products are gases. Delta H0 is minus 5691. Oh, yeah, we've looked at this one before, but they're going to ask us a different question, I guess. Delta H0 is minus 56.91. Yeah, and K is equal to 1.46 times 10 to the 6th at 25 degrees C. Okay. What would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume? This is Le Chatelier pure and simple because it says the temperature is constant. We're not changing the constant. We're only looking at the equilibrium position. Right? We don't even have to know what this is. This just says that most of it's over here, correct? So if we compress it, it's going to try to make what? fewer moles. If we decrease the volume, then there is less room for the microstates. So we make fewer of them. And to make fewer of them, you need to go to the side with the fewest moles. That's this side. This is 1.5. This is 1. So we would make more NO2 and decrease NO. Right? So there you go, decrease NO. Now, with an equilibrium constant of 10 to the 6th, there's not a whole lot of NO left. Right? But whatever's left will be moved that direction. All right, that was 36. That was too easy. Let's see if we can make a harder one. 46. 46. All right. Let's scroll down to 46. There we go. Oh, garbage man is here. $46. All right, what are the conditions? We're given the following data is given. Delta H of formation for the liquid, what is this? Formic acid, right? Right, that's the one that fire ants spit in their bite, along with the other things to make it burn so bad. And then there's the gas, and we're looking at the normal boiling point for formic acid, right? So we're looking at this process. There we go. And if we're looking at the boiling point, this is thermodynamically an equilibrium situation. Right? And when we say that, what we're referring to is this expression. Right? Right? So we need to calculate both the delta H and the delta S for the system. Right? And we use that, that same arrangement as we did for delta G earlier. Right? It's similar. For delta H, it would be delta H0 equals the sum of the delta H formation for all the products minus the delta H of formation for the reactants. Okay. In fact, we saw this one first semester, thermochemistry, I believe. We did this one. We could calculate the delta H for a reaction simply by knowing the formation for each one of these. Okay. So this one would be, what's the delta H for the product? That's the gas. The delta H is minus 363. And that's kilojoules. There's only 1 mole each, so it's only that many kilojoules. And then minus the delta H for the liquid, which is minus 410. Okay? So it's actually plus 410 minus 363. $47. So this one is plus 47 kilojoules. Now, if we use the same format for the delta S, we just say This is delta S, delta S, delta S. Right? Same arrangement. So the delta S for the product or the gas is 251. And notice for the delta S's for any of these, they're always positive. Why? Because they're based upon delta S, actually on the third law of thermodynamics. You know, when is delta S 0? Well, when you have a perfect crystal at 0K. So all delta S's, in fact, that should be a delta right there. That's an error. For product is 251. And this is joules per K minus 130. Okay. So 251.1 minus 130 is 12 point, see, we got a decimal out there, 12.1. No, excuse me, 121.1. That's better. 121.1. Joules per K. Okay, so this is kilojoules. So in order to put it into this equation, the delta S is fine. Delta S is 121.1 joules per K equals delta H, which has to be in joules. So it's going to be 47 times 10 to the third joules divided by T. Okay, so we'll put the T over here and we'll put the S over there. And the joules will cancel. The K is in the denominator. It flips into the numerator. We have the right temperature. So let's do 47. Let's see here. I need to say, there we go. And then divide by this one. I was just doing the change to joules in my calculator. There we go. 388 K. Okay. But the answer is in Celsius, right? Oh, okay. So we subtract 273. And I get positive 115. There we go. So let's see. Is it in there? Yep, there it is right there. All right. That was 46. Let's see. My board is, yeah, it's still on camera. Let me see. What else do I have marked off? 52 and 53. Did I lose somebody? Sounded like I may have. Justice, Cody, Jackie. No, there are 4. There's just somebody coming back online. 52. All right, let's scroll down. 52. Oops, too far. There we go. 52. All right. 52. Remember in thermochemistry again, when we were trying to determine the enthalpy of a target reaction, only we didn't want to actually do the reaction because it may have been hazardous. You know, if it was extremely exothermic, we could have an explosion on our hands. So we wanted beforehand, we wanted to theoretically see what is the delta H and what's the sign. Well, we used Hess's law, because Hess's law says, well, delta H is a state function, right? So you should be able to add equations together and calculate the delta H for the target reaction. We're taking that a step further. We're using the fact that you can add those equations together, and then we're combining the K's. So we extended this Hess's law further during our discussions of equilibrium. So in order to get the equation that we're looking for, here, this right there, excuse me, well, it's not going to behave. That one, and that one. In order to get that equation, we should be able to combine these two equations and find out what the K is. Now, why do we need the K? Well, look at the question. Calculate delta G0 for this reaction at 600 K using the following. Right? We've got two different types of Ks here, right? K temperature and K here, K, and Kp equilibrium. So what we're aiming at is we're trying to find value for K, because delta G 0 equals negative RT log K. We know the temperature, we know R. If we can find out what K is, we can calculate delta G for the reaction. All right. So first things first. We need to combine those equations. Right? So the first one is, well, let's see, what's the target? Let's put the target down here. H2O gas plus 1/2 O2 gas is in equilibrium with H2O2 gas. Right? Hydrogen peroxide. Okay. So we're going to work from the two equations that are just below that. H2 plus O2 is H2O2. Notice that this hydrogen peroxide in this reaction is on the correct side of the double barbed arrow. So we'll leave it there. H2 plus O2 yields H2O2. Yep, gas. And the K for this reaction is 2.3. Right, K 2.3 times 10 to the 6th. Okay, so we got this one right here. Actually, we got more than we need here. We only need a half. We got a whole. Look at the next equation. What direction is it pointing? Well, it's got water on the wrong side. Right? 2H2O, it's on the wrong side. So if we flip it, we can put 2H2O now is 2H2 gas, that's a gas, plus O2, gas. And now what does K become? When you invert the equation, you take the inverse of the K. So it would be 1 divided by 1.8 times 10 to the 37. Let's just do that calculation. 1.8 exponent 37, and then just take the inverse. 5.56, I'm going to keep an extra decimal, times 10 to the minus 38. 5.56 times 10 to the minus 38. So that's the new K for that reaction. Now, what else is wrong with this picture? Well, we only need one water. We got two. So what can we do? Well, we could take half of that reaction, right? One half of that would give us one water, one hydrogen, and one half of an oxygen. There we go. So now we got this one. We got that one already. We got this one. We've got a whole oxygen here, right? We're using this equation and this equation. We got a whole oxygen here and a half there subtracted from it. So now we got this one, right? Because that one drops out and this one comes down to a half. So we got everything we need, don't we? Hydrogens. Hydrogen, hydrogen. One hydrogen, one hydrogen. There we go. Now we just need, what do we do with the K's? Right? Well, we did the inverse already, but now we took a half of it. So what does it say? When we multiply by a constant factor, what does that do to the K? That becomes the power of the K. Right? So this would be to the 1/2 power, which means what in algebra? It means the square root. Anything to the fraction power is, well, 1/2 is a square root, 1/3 is a cube root, 1/4 is the fourth root, and so forth and so on. So all we need to do to that one now is just take the square root of it, which is 2.36 times 10 to the minus 19. 2.36 times 10 to the minus 19. Right? So this one has to be combined with this one. So when you combine equations, what happens to the K's? You multiply them. That one times that one is the K for this reaction. So I already got that one in my calculator. I'll just put the other one in there and multiply it. So I get 5.42 times 10 to the minus 13. 5.42 times 10 to the minus 13. There we go. Let's see. I got another one here. So now we got the K right here. We know the T, 600.1. We know R, we can calculate G. So this is going to be equal to 8.3145, that's a minus, times 600.1 K times log of 5.42 times 10 to the minus 13. That's the hard part. Now we just crunch numbers. Well, we've been crunching numbers all along, but this is the final crunch. 8.3145, change the sign. It's got to be negative. Then 600.1, and then I've already got it in my calculator, so I can just multiply it like that. Oops, what did I do wrong? I didn't take the log of it. So let's do that. 5.42 exponent, change sign, and then take the natural log. There we go. Now times 600. And times 8.3145, change sign. There. 1 point, let's see, we started off with, I can only keep two significant figures. 1.4 times 10 to the minus fifth, or 10 to the fifth. 1.4 times 10 to the fifth. And that should be joules, right? Our answer is in standard notation. What did I do wrong? Oh, it's saying I can keep three significant figures. All right. 1.41 then. 1.41. Okay, so that's going to be 1.41 times 10 to the squared kilojoules. And two places here, 141 kilojoules. All right, so that's why the answer is A. Okay, that was 52. Now we're going to move to 53. Let's see. Yeah, 53 is going to take a little calculating, but we have time. So let's make some room. And there. There we go. All right. Let's get it back on camera there. 53, I said, right? All right, let's scroll just a little bit to get the whole thing in here. 53. Okay, consider this reaction. 2NO2. 2NO2 gas yields N2O4. N2O4 gas. All right. Delta H. All right, we're given delta H as a negative. Negative. 56.8 kilojoules. Delta S is minus 175 joules per K. Okay, in a container at 298 K, so we know the temperature. And we know the partial pressures of each one. Let's be sure we get them in the right place. Okay, so it says initial N2O4 and NO2 are mixed with initial partial pressures of 2.4 and 0.42 respectively. That means the first one in this list is 2.4 atmospheres. And the second one in the list is 0.42. There we go. Okay. Which of the following statements is correct? Some N2O4 will decompose into NO2. It'll go this direction, backwards. Or NO2 will dimerize to form N2O4, forward direction. So the first one is backwards, the second one is forwards. The system is the equilibrium. Or the final total pressure must be known to answer this question. That's kind of dumb, isn't it? Well, no, it could be a question. Right? We only know the initial pressures, right? So we have to carry out the equilibrium reaction in order to find out what the total pressure is. But if we find one of these, none of these is true. If we find one of them is true, then that's the answer. So how do you tell what direction the reaction is going to go? Remember, think back to equilibrium. Calculate the Q. Do we know the K? Well, not yet. We can find the Q, right? We know what the expression is. Q would be this one divided by this one squared. So we can find the Q right now. And then once we find the K, we can compare them, and that'll tell us which direction the reaction is going to go. So 2.4, and then 0.42, square it first. So square it, and then divide that into 2.4. Is 13.6. 13.6. Okay. Remember, if Q is bigger than K, it goes that way. But if K is bigger than Q, it goes that way. Just a refresher. Okay, now how do we find K? Well, what do we know? All right, we know this expression, delta G 0 equals negative RT log K. Right, we know that one. But we don't know delta G yet, do we? Right? But we do have delta H, delta S, and T, right? So we could use this one. Right? That would give us delta G, which would go in there. Right? So if you want to, you can do this one first. Right? Pay attention to the units here. Right? You're going to have to convert that to joules and finish the reaction. And then take this value and plug it in here. Or we can use a math trick. If A equals B and B equals C, then A equals C. If A equals B and A also equals C, then B equals C. So negative RT log K is equal to delta H 0 minus T delta S 0. That's true, isn't it? If that's equal to that, and that's equal to that, they're equal to each other. That way we can do just one calculation. What are we looking for? We're looking for K, aren't we? So let's solve this for log K. We take this negative RT, we'll say delta H 0 minus T delta S 0 over negative RT. Now we can plug in the values. We know that one, that one, that one, that one, and still know that one, right? So we just plug in the values. Delta H in joules minus 56.8 times 10 to the third joules minus temperature 298 times delta S negative 175, right? And then divided by negative 8.3145 times 298. Why can't we cancel 298? I mean, temperature on the top, temperature on the bottom. Because this temperature is inside an add or subtract, right? It's not factored out. If we could factor a T out, yeah, we could cancel T, but not in this case. That T is buried in here. You can't get at it. So you have to put it in there separately. All right, So let's, this is going to be a positive number, 298, and 175 is 5.215 times 10 to the fourth is positive. And then we're going to add it to 56.8, change sign, negative, exponent 3. We'll add those two together. So I get a minus 4.65 times 10 to the third. And then we're divided by this group right here. So I got to multiply 8.3145, change sign, and 298 times, and then divide it into that previous number. $1.877. 1.877, and that's log K. So K, oops, be consistent here, K is equal to E to the 1.877. It's already in my calculator, so I'm just going to hit the right key. 6.53. K is 6.53. Now, let me be sure I didn't make a mistake. Okay. So now all we have to do is compare Q and K. K is 6.53. Q is 13.6. So Q is greater than K. So that means what? The reaction's going back this way. It's going back to NO2. So let's look at our choices. Some NO2, nope, N2O4 will decompose into NO2. A is the answer. Okay, that was a lot of work, but I don't see any other way to solve that problem. I think it was designed that way. Let me see if I make any comments here. Now, that's it. Now we're going to 53. Oh, that was 53, excuse me. 53. Let's see. Anything else? 56. Yep, we got time. 56. Back on camera there. 56. All right. Oops. Wrong one. 56. Here we go. Looks like my little black arrow slid out of place. Consider the following system at equilibrium. 56. Okay. PCl3 gas plus Cl2 gas at equilibrium. Actually, that should be a double barb. That would be PCl5 gas. Okay, 25 degrees. There we go. And delta H, we're given that also. Delta H equals negative 92.5 kilojoules at the same temperature. If the temperature of the system is raised, the ratio of the partial pressures of PCl5 to the partial pressure of PCl3 will what? Increase, decrease, stay the same? Impossible to tell, none of these. Okay. So we're looking at the ratio of PCl5 to PCl3. So we're this one divided by PCl3. What happens to that ratio? Up, down, no change. This one's simple. right? We know that if it's at equilibrium now, which it says it is, and the delta H is negative, it's exothermic. That means delta H goes on this side, right? And if the temperature of the system is raised, we're adding that component, which drives it back this way. So this one now is going down, this one's going up. So that means the total is going down. If you decrease the numerator and increase the denominator, then the quotient decreases. So the ratio decreases. There it is right there. B. 56. Okay, let's scroll down to 58. I think this one, we've seen this one before, with a different question attached. $58. Right? 58. Okay. All right. We're not asked for a specific value, so we're going to sort of reason this one out. The equilibrium constant for a dissociation, Cl2 to 2Cl, right, we've seen that one. Cl2, well, that's not working very good. Maybe brown will work. Cl2, there you go. I'll throw this one away. Cl2 just 2Cl. Okay. Measured, the K was measured as a function of temperature. Okay, so we got that graph again. 1 over T and log K. All right. A straight line with a slope of negative 1.651 times 10 to the 4th and a y-intercept of 14.53. 51. Okay, so this is the slope. Right. What do we know about this equation? If the slope is negative, the reaction is endothermic, right? Because the slope now is negative delta H 0 divided by R. So in order for the slope to be negative, delta H has to be positive. That's endothermic. So we got our answer right there. The reaction is endothermic. That was easy. Let's see. You can actually calculate the value, but you don't have to, not to answer the question. Last one, 59. Okay, 59. Next one. Okay. Okay, we've done one like this before. It's just worded a little different. For a certain process at 300 K, delta G, temperature equals 300 K. Delta G is minus 10.4 kilojoules. And delta H is equal to minus 7.0 kilojoules. Right, that's everything given. Now what's the question? if the process is carried out reversibly, the amount of useful work that can be performed, right? And that's the key. In thermodynamics, the maximum amount of work you can get equal to this value can only be obtained by a reversible process. And since all processes are essentially irreversible, except mathematically speaking, then your actual work will be less than that value, something less. I mean, for the original steam engines, it was like 2-3%. It was very inefficient. So they were losing here, and they were losing delta S also. But we've got some prototype gas engines now are up to 50% efficient, which is pretty good, actually. Okay, so the answer to the question is the amount of work that can be done is negative 10.4 kilojoules. Right there. Okay, what does that mean? If that's the work, negative 10.4 kilojoules, that's the work that can be done on the surroundings, right? Because your system and your surroundings are like this, and if the system does work on the surroundings, it's always negative. Okay, so that's good because the value is negative. Okay, that's all I have, I believe. Yep.